Welcome to Applied Business Analytics. In this short video, we discuss bias and variance. Suppose we have height and weight data, and we want to model a relationship between height and weight. We see that for low weights, the height's pretty low. Then for middle weights, the height goes up, seems to be a positive relationship. But then eventually, weight goes up, and you don't get taller and taller. You're just obese, unfortunately. So we want to model this relationship. Now, ideally, we are able to find the true mathematical relationship between height and weight. But that doesn't happen in practice. We collect data and we use some kind of modeling scheme. So we're going to look at fitting a regression line, and then we're going to look at fitting a polynomial and talk about the pros and cons of each type of approach to modeling this relationship. Of course, we need test and train data. So we split our data set randomly into test and train data. The blue dots are our training data, and the green dots will be our test data. Now we're going to leave the red line. That's the true relationship. We never really would see that in practice. We're going to leave that just so you can see how well our models are doing. So here is the training data set. We're going to fit a linear regression, the most simplest way of modeling a relationship between y and x. Regression lines, of course, can't bend. They're straight lines. And so this regression line really is not capturing the curvature we're seeing. And we say the inability for a machine learning method like linear regression to capture the true relationship is called bias. The straight line can't be curved. The true relationship is curved. The straight line can't be curved. So we'd say that the linear regression method has a relatively large amount of bias. In contrast, let's fit something that can curve, something that can be squiggly. So here we're connecting our dots, and you can see it's sort of a squiggly fit there. This is a 6-degree polynomial. The squiggly fit is super flexible. It hugs a training set exactly. And the squiggly fit can actually handle the arc in a true relationship, and we'd say this has very little bias. So the linear regression line has a lot of bias. The polynomial fit has very, very little bias. And we can compare how well the straight line and the squiggly line fit the data by calculating their sums of squares of residuals. Now, if you remember, the residual is y minus y hat, and that's the observed value, and this is what we call the fitted value. And over here, it's an exact fit. All the residuals are going to be 0, and over here, it's not exact. So the sum of the residual, so we compare things like we look at the sum of the residual squared, and the sum of residual squared over here is going to be 0, over here it's going to be bigger than 0, easily to compute the stuff in R. And you can see that the straight line does not fit the data set as well as the polynomial. But you might say, wait a minute, the polynomial actually looks like it's overfitting the training data. And you're right, the proof is in the pudding. The proof is not on this. The proof should be on our test data set. So we want to look at the test data set. And so what do we see happening here? So even though the squiggly line did a great job fitting the training set, it did a terrible job fitting the testing set. And in machine language lingo, the difference in fits between data sets is called variability. The squiggly line, the polynomial, has low bias since it's flexible, can adapt to the curve and the relationship between weight and height. But the squiggly line has high variability because it results in vastly different sums of squares for different data sets. Sometimes the squiggly line is going to do really well on the test data set. Sometimes it's going to do really horrible on the test data set. And it actually turns out that if I look at the sums of squares of the residuals, it's something like 3.2 over here and like 2.23 over here. It does horrible. That polynomial fit does horrible on the test data set. So it's hard to predict how well the polynomial will perform with future data sets. It might do well sometimes, and other times it might do terribly. It might do not well at all on future data sets. In contrast, the straight line, the linear regression fit over here, has relatively high bias since it cannot capture the curve and the relationship between weight and height. The straight line has relatively low variance. And what we mean by that is you're not going to be fantastic, but you're going to be consistently okay. That doesn't sound fantastic, but you're going to be consistently okay no matter what the test data set looks like. You're not going to get great predictions, but they'll be consistently good predictions. On the other hand, with a polynomial, you're not going to get consistently good predictions. Sometimes they'll be good predictions, but other times they'll be insanely bad predictions. So we say the squiggly line, the polynomial is overfit and has high variability, low bias. We say the regression line has high bias, low variability. And variability means consistently okay predictions in future data sets for the linear regression. For the polynomial, not consistently okay predictions on future data sets. In machine learning, the ideal algorithm has low bias and can accurately model the true relationship, and has low variability by producing consistent predictions across different data sets. How do we do this in practice? We're trying to find a sweet spot between a simple model and a complex model. And this is the bias variance trade-off people talk about. So there's different mechanisms people have learned, different processes, different modeling techniques people have to try to find a sweet spot, again, between simple models, complex models, to do this bias variance trade-off. And typical methods people use are what are called regularization methods. So there's things called ridge and lasso regression. And they also learn what are called tree-based models, random forests, that also help in dealing with this bias and variance trade-off. You don't want to be too simple, so you miss some obvious features that are going on. You don't want to overfit. You're trying to find a sweet spot between the bias and the variance.